Alright, we're here with the AP Calculus AB manual. We're looking at number 36, which is Log and Exponents Review. This is review because it should have been done in pre-calculus, but hey, it's necessary for calculus, so we're going to bring some of these old ideas back and see if we can start applying them to the things we've learned in calculus as well, see how we're going to use them. So the first thing that we're going to be looking at, oh, by the way, special thanks to Stu Schwartz for putting together the manual and letting everybody in the world use it for free. Things I'll be using today listed here, like you guys know from all the other videos. Let's get started. So the general idea is, as we've been looking through calculus, we've been dealing with polynomials, we've dealt with rational expressions, and we've dealt with trig. We haven't done a whole lot of exponential or logarithmic work. So now we're going to be looking at this idea of y equals a to the x and how to deal with that in the skills that we've used in calculus. Before we get to actual calculus skills, we need to review some of the algebra skills dealing with y equals a to the x. So let's get started. First of all, here's some pictures of exponential type functions: 2 to the x, 3 to the x, and 0.5 to the x, also known as 1/2 to the x. Something that you will notice immediately is that when a is greater than 1, because y equals a to the x, it's going to grow up, up. And when a is less than 1, it's going to decay, it's going to go down. Now if these were negatives, if a were negative for whatever reason, all it does is it takes the graph, if you have a negative on the outside, not if a were negative, if there's a negative multiplied on the outside, it flips the graph across the x-axis vertically. That's the only difference that you would see. Alright, so let's start taking a look at some more stuff here. The graph of various exponential curves were shown above. That's what we just looked at. One thing you need to remember though is y equals 1 to the x. When you have 1 to the power, 1 to any power, even 0 is 1. So it's just a constant. We know that the graph of y equals 1 to the x, graphs y equals 1. They're the same graph. If you don't believe me, check it with your calculator. And sometimes, when a is less than 0, will not exist at certain points. -2 to the 1/2 power. Why does that make sense? Because -2 to the 1/2 power is the same thing as this. Square root of a negative doesn't exist on the real numbers. It's imaginary. Therefore, we can't really deal with it. So we usually keep them positive. So when we look at these things, we want to see also not only how they're different, but what do they have in common. So the stuff that they have in common is the y-intercept, pretty much all the time, because y equals a to the 0 if x equals 0 gives us our y-intercept. What's anything to the 0 power? The y-intercept equals 1. What's the domain? Well, for all of these it's all real numbers, but what's the range? It usually needs to be greater than 0. Y is greater than 0. We don't have negatives typically unless we do something different to the function, like multiplying it by a negative and flipping it down into the negative sign. But anyways, let's get started going a little bit further. Let's look at some actual examples. One of the things that we need to understand is how to solve for these examples. Now, in order to solve an algebra equation dealing with exponents, it always helps us to notice something about the two bases. If we have a to the x equals a to the y, and if the bases are the same, then x equals y. Then the two powers are going to be the same. These two powers up here are going to equal each other. So what we have to do is change this equation relationship so that the two powers are the same. So when I look at this one, I see 2 to the x plus 1. And I want to ask myself, can I change this side so it has a base 2? Then what would the power be? The power in this case would be 3. Well, if 2 to the x plus 1 equals 2 to the 3, then that means that the two powers are going to be equal as well. So then x plus 1 equals 3. And it's just some algebra, x equals 2. Not too bad at all. This next one is very similar. If you start to look at it, you want to start to develop this instinct of what would the common base be. This side, 3 to the 2x minus 3, let's say that 3 is going to be my common base. Because this over here, a fraction 1/3, is the same as 3 to the negative 1. I'm going to make my pen a little bit skinnier, easier to read here. So this equals 3 to the negative 1. That means the base is the same, therefore the powers are the same, so 2x minus 3 equals negative 1. Add 3, do the algebra, you get 2x equals 2, x equals 1. It's easy to do the simple algebra. It's hard to set it up so that the bases are common. This one's a little bit different because if you think about 4 and 32, 32 doesn't really work as a power of 4, but it does work as a power of 2. In fact, 2 to the 5th power is 32. And instead of saying the third root here, I'm going to say the 1/3 power. On this side, I'm going to have 2 to the 2nd power instead of 4. And 5x minus 1 for the power. Now both of these have some similar algebra going on. What you need to realize is that when you have a power to a power, and a power to a power, same on the other side, you're going to multiply those. So this is going to be 2 times 5x minus 1. It's equal to 5 times 1/3. Now if I simplify all this, I get 10x minus 2 equals 5/3. Then I got some fancy algebra to do to get x by itself, but I'm actually going to stop there and let you guys do the algebra, because from here on, that's not even pre-calculus, that's algebra 1. You would add 2 to this side, which would be 6 over 3, so 5 plus 6 is 11/3. 10x equals 11/3. Divide by 10 times 1/10. So I get x equals 11 over 30. Sometimes your x is not going to be simple and easy. Now if I make a mistake somewhere in the middle, because I kind of did some of that in my head, I apologize. But go ahead and check the work for yourself and make sure it's correct. Don't just always trust the person you're watching. This one's similar to number 2. If you look at it, I have 7 to a power. 1 over 49 is really 7 to the negative 2. So I'm going to start out with that. I got 7 to the 2x plus 3 equals 7 to the negative 2 to the 3 minus x. Now remember, when you have power to power, you're going to multiply those things. So negative 2 times 3 minus x is going to be negative 6 plus x equals 2x plus 3. After subtracting an x from each side and subtracting 3 from each side, I'll have x equals negative 9. Again, this is simple algebra, but up here is the hard part, trying to match the bases. Okay, now this is kind of weird. It's not like the other 4 here. You got to think about, how do I make something to a power equal 1? So that means something to a power equals 1. Well, no matter what this base is, we know something about this power. Because anything to the 0 power equals 1. Then that tells me that this power right here has to equal 0. So 5 minus 2x equals 0. 2x equals 5. X equals 5 halves. So there we go.